Thank you to the organizers for bringing us all here. I think we all feel very lucky to be here. I would like to talk about some recent work that I've done in collaboration with Dr. Organizer Samantha Lin. The work is titled Dynamic Redundancy and Mortality in Stochastic Search. And the goal of this talk, the outline is to be able to motivate why we started working on this topic, give you describe the setting that we're working in, and tell you how we've been thinking about making progress in this topic. And I will show you some results, and I hope there'll be enough time for discussion. But while I have your attention right now, if there is one thing that I'd like for you to take away from this talk, I think the key idea here is that first passage problems, when the number of searchers are fluctuating, present a really exciting avenue for new research, for new tools to be developed, and they also help us answer a lot of new questions which we haven't been able to answer so far. One thing that I will not touch upon right now, but happy to talk about later, is when the number of searchers fluctuate, a lot of the commonly used techniques that we have can fail. And thus, it is important to think about new techniques. And I'm happy to discuss that in the question and answer session, or discuss it later with you. Okay. So to give you some motivation, it's always hard to motivate a first passage talk after Sid speaks. The only thing I have to offer is that there will be no starving bunnies, and I like graduate students. I won't be harsh on graduate students too. But just to motivate this a little bit, first passage processes are ubiquitous, and we've already seen in a bunch of examples, we've already seen a bunch of different examples that we've discussed already in this workshop: ligands binding to receptors, animal foraging for food, or even search and rescue operations. One thing that is abundantly clear from all of these examples is that there is a need to go beyond just looking at a single searcher searching for a target. In all of these examples, often you will have multiple searchers. So for example, if you have a bunny rabbit, even if it is searching for food, it is not only going to be a single bunny rabbit. There's going to be a bunch of them together who are going to be looking for food. And this has been well recognized so far. And people have talked about extreme first passage times already in this seminar. But just to note, this idea has been around for decades, and often people call it the redundancy principle when you have a bunch of independent parallel searchers trying to perform the same task. And the redundancy principle is, I think will also be a theme of some future talks that we will see. But this is where I want to motivate this talk, which is in a lot of these settings that we discussed above, searchers can dynamically join the search process, and they can also leave. So for example, when you have animals searching for food, it's not always the same set of animals searching. Animals can, leave the search process and can also join at later times. And this motivates us to think about the concept of dynamic redundancy beyond just simple redundancy, which is the process of dynamically joining the search. Coupled with this concept of mortality, which isn't as bad as it sounds. In this context, it just means that a searcher can abandon the search process and leave. And the goal of this talk is going to be to see how the combined effect of these two processes shape the extreme first passage statistics. Right. So let me just give you the setting that I'll be working in. So there is a domain where first passage is happening, of course, inspired by the Chicago bean. And there's a target within this domain. Let me be clear here that everything that I'm going to describe is also going to work for non-bean domains. In fact, you can also think about unbound domains, and everything that we are describing will still work. There is a searcher initially placed at some position x0. And for the time being, we'll just consider x0 to be a point, although it can be like a distribution over the whole domain also. And this is going to be the initial condition throughout this talk. We will always initialize a searcher at x0. And this guy is trying to, evolve, find the target, move around randomly. This is a continuous time Markov process. We are not making too many assumptions on the underlying search process over here yet. And at some rate, new searchers are added into the system at rate lambda. And this is the aspect of dynamic redundancy. Like new searchers are being introduced into the system, and they're always introduced in this case at x0. That is an assumption for now. And each searcher of the system can also independently die or abandon the process at rate mu. So this is the component of mortality. And now we're thinking about what does this quantity T lambda mu, which is the first time any of these particles hit the target. So this is going to be the quantity of interest for us right now, which is T lambda mu. And let's look at some limiting cases of this process. So when lambda is equal to 0 and mu is equal to 0, this is just the classic single particle first passage process that we all are familiar with. If you take the limit where lambda is 0, but mu is non-zero, we reach these single particle first passage processes under mortality, which is where you have a single searcher trying to find a target, but it can also die before it finds the target. And this has a very long history, and people have studied these particles with mortality for a really long time. But the opposite regime, where lambda is greater than 0, but mu is equal to 0, which is where searchers don't die, but they're being injected into the system at some rate. That is rather new, and people have only recently started thinking about how does the first passage statistics change when searchers are injected into the system. All of these examples that I cite over here are not examples which are related to necessarily time homogeneous recruitment or addition into the system, but they all somehow talk about this concept of dynamic redundancy or injection of particles into the system and how the first passage time statistics change. The focus in this talk will be this regime where lambda is greater than 0 and mu is greater than 0. And we are interested in the statistics of T lambda mu. So just jump to an important result, which is that the statistics of T lambda mu, which is the extreme first passage time, can be summarized by this thing called the survival probability, which is the probability that none of the particles have hit the target up till time t. And the nice thing about this expression that we can write is that the statistics of T lambda mu can be expressed in terms of the single particle statistics. So if we can solve for the single particle dynamics of this process, we can solve the full problem and get a lot of exact results from this. So let us just quickly move to a simple example of the domain being unbounded. So you think about the half line where there's a target at the origin. Particles are being injected at site x0, and they can also die independently wherever they are at rate mu. And we want to see the first time any of the particles hit the origin. Well, using the formula, we can get an expression for the survival probability. But even in this very simple case, it doesn't seem immediately very insightful. So one wonders, what is it that one can do about this process? Well, you can actually take this expression of the survival probability and do a lot of asymptotics and try to get insights from it. But what we decided to do was something different. We instead thought, okay, let us try to create bounds on the first passage time. Is there a way in which we can bound the first passage time from below and above in a rather simple fashion? And if there is a second thing that I want you all to remember from this talk, that would be probably this equation, not an equation, but you have these inequalities over here, where I'm saying that the expected value of T lambda mu can be bounded from above and below by these quantities which only depend on lambda and mu. And let me define what I mean by p mu over here. So p mu is this very special type of is a very special quantity. It relates only to the single particle dynamics under mortality. If you think about any particle in isolation and ask what is the probability that this particle, without any other searchers, finds the target before it dies? Well, that quantity is exactly this p mu, and like it can be computed as follows over here, where this small f is the first passage time density of the single particle. And this is essentially the probability that the single particle finds the target at time t. This exponential minus mu t is the probability that it doesn't die until then. And you just integrate over all time. And this gives you the probability that it ever finds the target before it dies. And if there are any questions, like feel free to stop me, because I'm now going to maybe talk about how one may see these bounds arise through like some simple arguments. And I'm going to guide you through the calculation, but okay, let's look at the lower bound first. The intuition that I'm going to give you right now is also going to work for higher moments of the quantity t lambda mu. I'm just focusing on the mean right now, but like the same intuition that we use to create bounds over here are going to work for higher moments. So let us think about this process in time, where at time t equal to 0, we have one searcher that begins the search process. If this searcher was, isolated, independent, with probability p mu, it would find the target before it dies, and with probability 1 minus p mu, it doesn't. Let us say that it doesn't find the target before it dies. And then there are more searchers injected at different times. Like, okay, these ones also could not find the target, but this fourth guy was able to find the target, or would be able to find the target if like the process continues forever. Well, the mean first passage time cannot be greater than the mean recruitment time for the first potentially successful searcher. So this is like a calculation which you can do in a few steps, but let me just tell you the result over here, which is that this is going to, so the index of the first potentially successful searcher is going to follow a geometric distribution, and then the mean number of recruits that need to happen for the first successful searcher to be born is given by this quantity 1 minus p mu over p mu. And the mean recruitment time is just 1 over lambda, the inter-recruitment time. And using just these two, we get the lower bound, which is the mean time taken for the first potentially successful searcher to be recruited. And using the same intuition, we can also talk about the upper bound. If you look at it, the upper bound is only the lower bound plus some quantity, even though it seems like it is, minus something. Log p mu is going to be decreasing in mu, so this is going to be a positive contribution on the whole. And this additional term is nothing but the conditioned first passage time, mean first passage time of a mortal particle, right? And why it is an upper bound and not the exact mean first passage time? The argument for that is simple, which is, suppose you have this successful searcher that succeeds. So it's going to succeed at some point. Let us suppose that it succeeds at this pink spot over here in time. It is possible that a particle is born later, but is able to succeed before this particle. And that is why this estimate that we have from the upper bound is is an overestimate of the mean first passage time. And in principle, the mean first passage time can be smaller than this. Well, we can already get some insights from this, but let me just repeat the idea of these bounds. The lower bound is the time for the first potentially successful searcher to be born. And the upper bound is obtained by computing the conditioned first passage time that that particle is able to find the target. Right? So let us see what these things tell us immediately. Well, the first thing that this upper bound is able to tell us is that the mean first passage time for this process is going to be finite for all finite lambda and mu because we've been able to bound it from above. And this is rather surprising because if you think about processes which have like an infinite mean first passage time, like a single particle Brownian motion, and even when lambda is much, much smaller than mu, which is the regime where there are less than one particle on average in the system, what this says is that the mean first passage time is still going to be finite. And next, I just want to point out that this bound, the upper bound that we've computed, is actually not that bad. It is, in fact, the best that we can do generally, because this upper bound is the exact mean first passage time for a DRM process, which is like dynamical redundancy and mortality, when the underlying first passage time is a deterministic value. So if you consider a particle which deterministically moves to the target, so if it doesn't die before reaching the target, it finds the target at a fixed time. For that process, like this is going to be the exact mean first passage time. So which also means that this bound is optimal in some way. All right. Okay. Another interesting thing about the lower bound now is instead of thinking about lambda and mu as independent parameters, let us think about them as being correlated. For example, here right now, I'm taking both the values to be equal to R. So this is a situation where lambda equals mu equals R. Well, this is what the process looks like that. Looks like then. So at some rate, R particles are being injected into the system. At some rate, R, they're dying. On an average, there's one particle searching for the target, and at some point, the target is found. Well, this description sounds very similar to this process where you only have a single particle starting from this position x0, and at some rate, it resets to this point x0. So it is diffusing around, and at some rate, it decides to abandon its trajectory, start again from x0, and start a new process. So in this process, also on an average, there is one searcher at every time. In fact, there is exactly one searcher at all times, and it is able to find the target in some time. An interesting thing to note was that this quantity that we are writing over here is exactly the mean first passage time of a single particle undergoing this stochastic resetting at rate r, which allows us to conclude that stochastic resetting provides a universal lower bound to this balanced process where the injection rate and mortality rate are equal. And this was just nice to note. And here is like a plot where we show both the bounds together. The blue line over here is the exact mean first passage time of this process with dynamical redundancy and mortality. The red line, this red curve over here, corresponds to the lower bound and also the mean first passage time of a particle undergoing resetting. And you see that the upper bound, so here is denoted is colored in yellow, and it very closely follows the. So it's not a bad upper bound. This is all I'm trying to convey over here. And one nice thing about this, which you can notice from this equation directly, is that as R becomes large, this second term in this upper bound goes to 0 as 1 over square root R. And the lower bound and upper bound sort of squeeze together, sandwich, and converge to each other, which also allows us to see that the mean first passage time of this DRM process in the high turnover limit, where I'm talking about, like where I'm calling when you have like injection and mortality are rapid, I'm calling that the high turnover limit, and we are able to see that we can get the exact in this limit of r tending to infinity, we can get the exact value of the mean first passage time. And if you go back to the upper bound that we have over here, quite generically, like the second term goes to zero. Like the only time it doesn't go to zero is when like you have particles which have finite speed, or if you have like a sharp threshold for the first passage time below which the probability is zero. Only in those cases does this term not go to zero. And that allows us to establish, quite generally, the high turnover behavior for the mean first passage time in this case. And one thing that we've been working on and we're quite excited by right now is the fact that this random variable TR, R, which is the first passage time when the recruitment rate and mortality rate are both R, is actually an exponential random variable with rate RPR. It's not just that the mean looks like an exponential random variable with mean RPR, but the whole distribution is actually exponential. So in the last few minutes, I'd like to maybe describe this figure to you, which is we don't have to keep the mortality and the recruitment to be equal. Instead, let's consider this parameterization where lambda is alpha R and mu is equal to R. We just discussed that when alpha is equal to 1, resetting is always faster than this process with redundancy and mortality. And you can see that over here in this red curve, where as you increase R, this is the y-axis is the ratio of the mean first passage time of this process versus the mean first passage time of the resetting process. And the red curve always stays above 1 and converges to 1 eventually for large R. But very interestingly, you can show that for any alpha between 1 and phi, where phi is the golden ratio right now, DRM eventually becomes faster. So this process eventually becomes faster than resetting in the high turnover limit. And when alpha is greater than phi, this process with dynamic redundancy and mortality is always faster than resetting, which is this yellow curve over here. And phi is the golden ratio. And let me just add this caveat that this result is only true for the 1D Brownian case. Like I'm not so we don't have a general result for what the value should be when you change the process from like 1D Brownian to something else. But this seems to be the case for the 1D Brownian motion. And just like a small comment about mu equal to 0 is actually very different from alpha being greater than 1, much greater than 1. When alpha is much greater than 1, like redundancy dominates. But what we show over here is that like the two processes, mu equal to 0 and alpha much, much greater than 1, have very distinct properties. And this dashed curve over here is the no mortality mu equal to 0 case, which is taken from this paper. And I think you're going to hear more about this paper later in this week. So let me just end with, in the 2 minutes, in the 1 minute that I have, let me just end with this discussion. Okay, so like this is the summary. This is all we need to know to, ask questions and discuss further. This is like a summary of the talk. This is the reference where you can find a bunch of things that I described today. We also have the great pleasure of listening to Professor Boyer talk about his recent work on these stochastic synthesis and degradation processes, which will be right next. And also, like a couple of weeks ago, like people have started also thinking about like these problems where like searchers can join and exit, and they've called it intermittent entries and exits. So far, like I think the nomenclature is pretty all over the place in the sense that like people have used terms like injection, immigration, emission, dynamic redundancy, and entries to talk about roughly the same thing. And if you look at the other end of mortality, it's even more scattered because different applications require different nomenclature. But I hope like when I think a bunch of people who are working on these topics are here in this meeting right now, and we can have like a conversation about how we should be proceeding further. I would just like to end with by thanking my collaborator, Dr. Samantha Lin, and I'm very happy to like discuss right now, answer questions, or even in the coffee breaks. Time for questions?
Questions?
Maybe I missed the basic point, but like, you have this parameter alpha, and I forget which one was where like recruitment wins over like mortality, but in the mortality dominated limit, then you may not reach the target. Is that correct?
So when alpha is less than 1, mortality dominates,
right.
Because lambda was defined as alpha r,
right.
And still the mean first passage time is going to be finite.
But what about what walkers don't make it? Are they excluded from the ensemble?
They're not excluded from the ensemble, but the thing is that there are walkers that don't make it, but there's also an injection which is much smaller.
Okay, I got it.
Yeah. And that leads to a finite MFPD overall. Yeah.
So in kind of what you presented today, you're thinking about X naught being a single determinant point.
Yes.
You explored X naught being drawn from a distribution.
We haven't explored it yet. I believe that even some qualitative results can change when the particle is initialized from a distribution, let's say uniformly spread over a confined domain, than a single point. But like the same formulas that we're using over here can be generalized directly to those situations. We haven't explored that yet.
Right. So in general, you would probably expect it to depend on the support of that distribution, whether it can touch the target.
Yeah. And I think we already know that in not the dynamic redundancy case, but just the n particle system, like you get different answers for the fastest FPT when you have particles starting from the same point or from a distributed set of points.
Questions? We have one quick one. The intuition for this minimum that you had in TRR, right? Is that on the left end? Is it just because you have to wait for a while for the first particle to? Do you start? What's the initial condition? Do you start with a particle?
You start with 1.
You start with 1.
Yes.
So what's the intuition for the minimum?
So
see the right hand side, right? That's where you just die so often.
Exactly.
Yeah, okay, but the left.
But the left is so when mortality is small enough that even one particle can potentially find the target.
Yeah.
But also you're increasing injection as well. So you're increasing the redundancy in the sense that you're adding more and more particles more quickly. So there is this regime where the mean first passage time actually decreases, where the role of redundancy dominates the role of mortality, because mortality is still small enough that it doesn't really play that big of a role in like completely changing the qualitative statistics of the mean first passage time. Yeah.
Your mortality and your recruitment process, I guess they're always exponential weight, like the mortality is an exponential waiting time.
Yeah.
It seems like your theory is pretty generic though. Could you treat cases where the mortality is some non-exponential, peaked away from 0 waiting time?
So everything that, so all of those details are in the quantity P mu, which was the probability of success for an individual particle.
Yeah.
As that distribution changes, P mu will change, but we can compute that based on the distribution and still get everything. I think things get trickier when injections become non-exponential, and injections are, Markovian processes. So Sean Lawley and Ray have been working on time inhomogeneous Poisson recruitments, but I think still working with arbitrary distributions is a little challenging.
Right. Thanks again. Yeah.